Hello everyone, I'm Dr. Nandy. Welcome to the YouTube channel Ecstasy of Physics. I'm come with another video of AP Physics 1 series. In this video, we'll be going to talk about the multiple choice questions of circular motions and gravitations, what we have got in the past papers. Generally, AP Physics 1 algebra-based course has 10 different units, among which it is circular motions and gravitations, that is the third unit. And this multiple choice question, it generally exam weighting of circular motions and gravitations is around 4 to 6%. In this question is given that a mass m moves on a curved path from the point x to the point y. Which of the following diagram indicates the possible combinations of the net force F on the mass and the velocity v and the acceleration a of the mass at the location? So the curved path section, it is given that it is the point x to the point y. So the point x to the point y. Now let's analyze the options one by one. In the first case, we are having the net force F on the mass, the velocity v and the acceleration a of the mass. So in the first case, they have given the directions of accelerations and the directions of velocity, it is same. So always the object velocity directions, it would be tangential to the directions of motions, means of the path, it would be having the tangential velocity. So it cannot be at the same directions in case of circular motion, because here the path, it would be curved path, it would be kind of a circular section, it is parts of this arc of a circle. So in that case, it would be having the accelerations towards the radially inward, but the velocity, it should be along the tangential directions. Now that point is not matched, so that means A cannot be the answer. Now in case of B, it's given that velocity, it is going inside towards the radially inward directions, but the accelerations, it is along the tangential directions. So which is not possible. In case of circular motions, there would be a certain amount of centripetal accelerations. It might be have some tangential acceleration also, but there would be the presence of centripetal acceleration, which is not shown at the point at this section here. So that would be not the answer. Now let's analyze the option C. Now in case of the option C, the motions, that means the velocity, it is shown along the tangential direction, that is correct, and the accelerations and the force, both are exerted in the opposite direction. But we know from the Newton's second laws of motion, the directions of the applied force, that is same as the directions of acceleration, which means that cannot be in the opposite directions to each other. Net force directions, it will be always towards the directions of acceleration. So this is also not possible due to that consideration. That means the only consideration is that acceleration's directions, it is same as the directions of force and the velocity along the tangential directions. But note that here the directions of acceleration, it would be not exactly to the radially inward directions. So from there we can conclude that it would be having certain amount of tangential acceleration as well. Means tangential acceleration means we can consider, let's say this is representing the circle, and in that case during its rotation we have already learned that there would be a centripetal acceleration towards radially inward directions exerted. That's called the radial acceleration as well. And we have considered that the motion, that is uniform circular motion. But what will happen if it is a non-uniform circular motion? Non-uniform circular motion means this omega, angular velocity, it should not be constant in case of circular motion. And we know that velocity, tangential velocity, that can be represented by angular velocity times by the radius. R is the radius of the circle. So if omega doesn't constant, that means that v, this is also not a constant. So in that case there would be accelerations along the tangential directions, and that acceleration is known as the tangential acceleration, AT. It representing the tangential acceleration, and the expressions of tangential acceleration, that is delta v upon delta t, means change in the magnitude of the tangential velocity per unit of time, and that accelerations it would be exerted along the tangential directions of the circle at. And combinedly, if we consider, we know that acceleration is a vector quantity, so at this point the object will be having the centripetal acceleration towards the radially inward directions towards the center of the circle. It is having the tangential accelerations, and combined effect of the centripetal and tangential acceleration, it would be along this direction. So A, that's the resultant acceleration, and that's what actually it's given here, the resultant acceleration. So this D would be the correct answer here. So in this question, it's given that a ball attached to a string is whirled around in a horizontal circle having radius r. If the radius of the circle is changed to 4r and the same centripetal force is applied by the string, the new speed of the ball is which of the following? So here we have two diagrams. So in the first case, the radius r and the mass of the ball we have considered, that is equal to m. It is revolving with respect to the center O. In the second case, the radius is 4r. Now in the same in these two cases, we have to maintain the same centripetal force is applied by the string. The expressions of the centripetal force, that is m into v square upon r, and that is going to be applied by the string. That means T equal to m v square upon r. The new speed of the ball is which of the following? So this is the first expressions. Now in the second expressions, so it is corresponding to the first circle. Now in the second one, let's consider the speed. It has become the v prime. So it is m into v prime square upon 4r, and that is equal to the tension we have to maintain, that would be same. Tension it would be same. So from there we can equate this to relation, that m v square upon r, and that is equal to m v prime square upon 4r. So finally this m r it is cancelled out. So v prime square, that is equal to 4 v square, and from there we can say v prime equal to 2 into v if we do the square root in both sides. That means that finally the speed is become twice the original speed. So in the next question, a racing car is moving around the circular track of radius 300 meter shown above. At the instant when the car's velocity is directed due east and its acceleration is directed due south, has a magnitude of 3 meter per second squared. So when viewed from above, the car is moving. So among the four options, which option is correct? So here the conditions is given that the car's velocity is directed due east. If you are going to draw that, the car's velocity is directed due east, so along this direction that velocity will be represented, and its accelerations is directed due south. Accelerations is directed due south. So this would be the directions of acceleration, and has a magnitude of 3 meter per second square. So A equal to is 3 meter per second square. When viewed from above, the car is moving, and the radius is given as, that is equal to 300 meter. R equal to 300 meter, and acceleration A equal to 3 meter per second square. Generally the acceleration they are talking about, it's a centripetal acceleration because it's a rotating in a circular track, and we know that centripetal acceleration, expressions of centripetal acceleration, that is equal to v square upon r, that is equal to 3. So from there we can say v square equal to 3 into r. Presently r is given as, that is 300 meter. So 3 times 300, that is equal to v square. that is 900, which means we can say square root of 900, that is 30 meter per second. So we have got the velocity value, that is 30 meter per second. Now let's look at the options. Among the 4 options we are having A and C. Both are having the car is moving, both are giving the velocity 30 meter per second. Now we have to determine whether it will be clockwise or anti-clockwise. Here we can define it should be you can consider, let's consider it would be the counterclockwise direction. So if it is like counterclockwise direction, so any of the positions we can consider. Let's say this position. So in that case the velocity it would be upward, and its acceleration directions it would be towards the center of the circle. If it will be located here, then in that case, in case of counterclockwise directions, it would be velocity it will be towards west, and its directions it will be towards its directions of acceleration towards the south. So here the directions of accelerations it is matched, but the directions of velocity it's not matched. That means if we are going to consider in clockwise directions at the same point, so we can consider if the car is moving in clockwise directions, and at the same point if we draw the velocity vector, it would be along the tangential directions, and it would be towards the east, and its centripetal accelerations towards the center of the circle, that is representing the south. That means the final answer it will be the clockwise at 30 meter per second. In this question, an automobile moves at constant speed down one hill and up another hill, along the smoothly curved surface shown above. Which of the following diagrams best represents the directions of the velocity and the accelerations of the automobile at the instant that it is the lowest point as shown? So it's moving towards these directions, right? Because it's shown here. That means if it is moving along this direction, so we can determine that velocity it would be along the tangential directions, and since it is like it is at the down part of the curved part of any slope, it is at the down, and it is just beginning at the slope of the next hill. So in that case it will be having the accelerations, means just look at the path, it will be a semicircular path, and so in that case the acceleration towards the radially inward direction. So now let's check the options where the velocities and accelerations are matching. So it's velocity and acceleration matching in case of B. In this question it's given that a child has a toy tied to the end of a string and wheels the toy at constant speed in a horizontal circular path of radius r. The toy completes each revolutions of its motions in a time period of t. What is the magnitude of the accelerations of the toy? This is representing a horizontal circular path, and toy is tied by a help of a string. So here the tension exerted to the radially inward directions, and the radius of the circular path is given as, that is equal to r, and the time period that is considered as t. So let's consider the t stands for the time period, and that will be the tension exerted, that can be represented by ft. Now the time period means it's basically representing that it's the time taken for one complete revolution, that's known as the time period. What is the magnitude of the accelerations of the toy? Accelerations of the toy, it is nothing but the centripetal acceleration. Expressions of centripetal acceleration that can be represented by is v square upon r, where v stands for the tangential velocity. This v it can be represented as, if it is rotating in anti-clockwise direction, then along the tangential direction the v would be represented, or this v it can be represented in terms of angular velocity as well. So that would be, we know that v equal to omega times r. We can substitute in this equation, omega is the angular velocity times by the radius whole square upon r. So finally we are getting the other expressions of centripetal acceleration, that is omega square times r. Again, angular velocity is linked with the time period by the formula that 2 pi by t. So you can substitute in this formula that omega equal to 2 pi upon t, where t stands for the time period whole squared times by r. Then we'll be getting it is 4 pi squared into r upon t squared. So that's the expressions of the centripetal acceleration. So magnitude of the acceleration, it is matching with the option B. In the next question, a compressed spring mounted on a disc can project a small ball when the disc is not rotating as shown in the top view above. The ball moves radially outward. So this is the diagram is given when the disc is not rotating and the spring which is mounted on a disc, and from there a ball which is basically coming out in radially outward directions. At present in the top view what is given, ball is not rotating condition. Now the disc means the disc is not rotating condition. Now the disc then rotates in counterclockwise direction. So it started rotating in counterclockwise directions as seen from above, and the ball is projected outward at the instant the disc in the position above shown above. So now the next 4 options are also given corresponding to the positions of the first one, but with the disc rotation. Which of the following best shows the subsequent path of the ball relative to the ground? So the first top view is given without rotation, and the next options are given with rotation. Now what could be the subsequent path of the ball relative to the ground? Due to the compression of the spring, it was moving in radially outward directions with certain velocity. And now since the disc it is in rotating condition, it will be having some tangential velocity as well. And the directions of tangential velocity, it would be rotating in counterclockwise direction. It's given here. It's rotating in counterclockwise direction. That means the directions of tangential velocity at this point, it would be upward. That will be the tangential velocity, and this velocity it is introduced due to the spring. We have to consider the resultant of that. So this resultant, it would be along this direction. That would be representing the resultant velocity, and that resultant velocity directions will be representing the path of the motions of the object. So it is matching with the options D. So here it is given a ball of mass m is attached to the end of a string of length q as shown above. The ball is released from rest from position P, where the string is horizontal and it swings through a position Q. So its length should be L. According to the given diagram, its length should be L, not Q. Q is this end position. So it swings through position Q. It swings through the position O. O is the center of the circle. It swings through the position O, where the string is vertical, and then to positions R. So then after that it comes back to the position R, where the string is again horizontal. What are the directions of the acceleration vectors of the ball at positions Q and R? So at positions Q and R, what would be the directions of accelerations vector of the ball? That we have to determine. At the positions Q and at the position R. Initially ball, it has started its motions from the point P. Once it is reaching to the point Q, it will be having the tangential velocity along these directions. That is representing the tangential velocity, and since it's continuing the rotational motions, it will be having the centripetal acceleration to the radially inward direction. So that would be the centripetal acceleration. And once it has reached to the point R, that is the extreme position, and it has started its motions from the point P and it is released from rest, that means the velocity at the point P, it is 0. Similarly, when it has reached at the point R, at that point also the object comes to rest instantaneously, that means the velocity it would be 0. If the velocity it would be 0, we know that acceleration, centripetal acceleration expression, that is v square by r. If there is no velocity, there would be no centripetal acceleration. That means at that point, since the object is having the mass m, in that case it will be having the gravitational acceleration only in downward direction, that would be g. So now from here, let's choose the option. So at the position Q, we have mentioned that it would be having the centripetal acceleration. Now you can ask that at the Q point, then what about the gravitational acceleration? Definitely at the Q point there would be the gravitational accelerations downward. But the thing is, the net acceleration, it would be towards the radially inward. So that's why the accelerations directions of net acceleration, it is upward. So here at the position Q, the accelerations, it would be upward. So either it would be C or D. And now let's check the options for positions R. At the position R, it would be only gravitational acceleration. So it would be downward. It would be downward. So the option, that is C.